So the plot for all these sample problems is that I want to have some target amount in my bank account after capital N years. So the amount A is a function of the number of years N, and I'm going to assume an interest rate R. In the context of this course, that's always the exponent in e to the RT. We're talking only about continuously compounded interest. So let's look at the easiest version of this problem. My rich uncle is going to give me some initial deposit, A of 0, and all I have to do is specify the right amount, and here's how I figure that out. I say that if I start with A of 0 in my bank account, and it grows for n years at an interest rate of R, I want that to come out to be A of n, and therefore the amount that I need, A of 0, is just A of n times e to the minus Rn. In other words, I take the final amount I want and discount it by the appropriate factor. Okay, here's an alternative way. My bank is willing to compound my deposit annually at a certain rate S, which means that in 1 year, $1 turns into 1 plus S dollars. But I have to wait the full year in order to collect that amount. The alternative is continuous compounding. With continuous compounding, $1 turns into e to the R dollars after 1 year. And therefore, in order for these to be equivalent, 1 plus S has to equal e to the R, or the interest rate the bank has to pay is e to the R minus 1. Here's a nice way of looking at that in terms of Taylor series. What is e to the R minus 1? Well, e to the R is 1 plus R squared divided by 2 factorial plus R cubed divided by 3 factorial, and so on. And then I have to subtract 1 from that, so what's left over is R plus R squared over 2 plus change. In other words, with interest compounded only annually, you need an amount S that's approximately R plus R squared over 2.